the properties of radicals. Remember that we can go between radical form and rational exponent form. So the majority of this lecture will be dealing with the radical form and how to work with that. And the first one is the product property. You guys are familiar with this from square roots. There's nothing different between square roots, really, and what we're going to have with these more advanced roots that have indexes of 3 and 4 or whatever, that if I have something and it's underneath a radical sign and the index is n, that I can break that up into two separate roots, each with the index of n. I could break what's underneath that radical up, or I can combine them. Doesn't really matter. And the same thing is if I have something that has a numerator and denominator all to the index or to the nth, taking the nth root, that I could split them up into two separate numerator and denominator radicals, or I can combine them. Doesn't really matter. Whatever best for me. So here's an example. If I had the cube root of 4 times the cube root of 2, I can combine those together and give me the cube root of 8, which is 2. Or here's a situation where I have the 4th root of 162 and the 4th root of 2, that if I wanted to, I could combine those into one big fraction, then divide the denominator into the numerator. If that looks like that would be an easier way to simplify it, in this case it would be. So let's go through a couple simplification examples. The first one would be a cube root of 12 and a cube root of 18. Now, the only time I could combine those is if they are the same index. For example, if I had the cube root of 12 times the 5th root of 18, you could not combine those under one radical because the indexes are different. They need to be the same. So in this case, they're both cube roots. So there are two ways I could work this. It depends on what way you want to do. You can combine those and take the cube root of 12 times 18 underneath one radical, which would be the cube root of 216, and that would be 6. Another way you could work it is if you didn't want to worry about 216, is you could probably break that up, or you could break that up into its factors, and once you combine those two, you could say 12 is 2 times 3 times 2. That would be 12, and 18 would be 2 times 3 times 3. Then if we look at that, we've got 3 2's, so that would be 2 cubed times 3 cubed. These are cube roots. And so the cube root of 2 would be 2, the cube root of 3 would be 3, and that would be equal to 6. So you could simplify it out or go with the bigger number like 216. The next one is the 4th root of 80 over 5. So when I approach this, one thing to know is you can never have a radical in the denominator. So that 4th root of 5 has to go. It can't stay that way. If I could divide the 5 into the 80 evenly, then that's going to get rid of my denominator. So I look at the indexes. This one's a 4, that's a 4. So they could combine under 1 if I wanted to. Since 5 divides evenly into 80, that's going to be the approach I'm going to take. So I'm going to combine 80 and 5 under one radical. And then 5 divided into 80 is 16. So I get the 4th root of 16, which would be equal to 2. Another example is I have the cube root of 4 and the cube root of 128. They have the same index, both 3, so those could combine under one radical. Okay, so I made a little correction. That was a 4, not a 3. So 4 times 128 is equal to the cube root of 512, which is equal to 8. Okay, moving down to the next one. They both have an index of 5, so they could combine under one radical, and I would do that if the 6 divides evenly into 192. That gets rid of my denominator, and it does. So I'm going to combine them under one single radical, and then 6 divides into 192 32 times, and so that would be not 2. That would be 2. Okay? Let's go to the next topic. Like we had before, you cannot have radicals in the denominator. So here's a list of things that you can't have when you say, or you need to simplify so that these don't exist. Number 1, you can't have any perfect squares or not perfect squares, but you can't have any perfect powers underneath the radical sign. So for example, if I had a cube root like I have here in A, I can't have any perfect cubes in there. So whatever the index is of the radical, I can't have perfect powers of that under the radical. I also can't have any fractions underneath the radical sign, and I can't have any radicals in the denominator. So with that in mind, let's go ahead and try to simplify these. So I have 135. Okay, so for 135, I can think of that as the cube root of 27 times 5. And then the cube root of 27 is 3. So this is going to be 3 times the cube root of 5. Okay, looking at the next one. What I have is I have an index of 5 for both of those, so those could combine under the same fraction. So I could have the 5th root of 7/8. But that's not going to get rid of my denominator because 8 does not divide evenly into 7. So when I have that situation, what I'm going to have to do is rationalize the denominator. So what I say to myself, I'm going to say, okay, I have the 5th root of 8. Where's my next perfect 5th power? So I'm thinking to myself, what can I multiply 8 by that gives me a perfect 5th power? And I know that 2 to the 5th is equal to 32. So if I can get what's under the radical equal to 32, then I will have no radical in the denominator. So I look and see that I have an 8, and if I multiply both the top and the bottom by the 5th root of 4, it has to be the 5th root because that's what my index is of my radical on the denominator, right? I need to combine the 4 with the 8 under one root sign. And the only way to do that is if they're both 5th roots. So now that I have multiplying the numerator and the denominator by the same number, my numerator is going to be the 5th root of 28. My denominator is going to be the 5th root of 32. So I'm going to have the 5th root of 28, and my denominator will be 2. So I didn't change its value, but I changed the form so that I don't have a radical in the denominator. Let's look at the next one. I got the cube root of 500. So I'm thinking to myself, what's a perfect cube? And 125 is, so I can take this and I can say that is the cube root of 125 times 4. And we know that the cube root of 125 is 5. So this would be 5 times the cube root of 4. Moving down to our letter D, I have a situation again where I would like to be able to divide the denominator into the numerator. They both have the same index, but I can't. So the only way I'm going to simplify this one is by rationalizing the denominator. So I'm thinking to myself, it's a 4th power. My next perfect 4th root would be 16, which would be 2 to the 4th is 16. So I'm going to make what's under my denominator, the radical in my denominator, be 16. So I would have to multiply the numerator by the 4th root of 16. The 4th root of 4. And the denominator by the 4th root of 4. So now my numerator is going to be 76. And my denominator will be the 4th root of 16. There is no perfect 4th power that I could pull out of 76. So that's as simple as it's going to get, and my denominator would be 4. Actually, there was a mistake in this last one. The fourth root of 16 is 2, not 4, so let's change that. Okay, let's go to the next topic. And I'm just going to blow right through this. I already mentioned it. What I said is, how do you know when you should divide and when you should rationalize? Well, I mentioned before, they both have to have the same index. But if the denominator can divide evenly into the numerator, by dividing the denominator into the numerator underneath one radical, well, I've got rid of the denominator. I don't have to rationalize it. And if I can't, well, then I'm going to have to rationalize the denominator. So that's kind of how you decide. All right, so now we got another situation here. We have a radical in the denominator, and we have a it's added to something. So how do I get rid of this radical? Well, what I'm going to do is I'm going to multiply both the numerator and the denominator by the conjugate, just like we did when we had imaginary numbers. So what I want to do here is I'm going to multiply the numerator times the conjugate of the denominator. That would be 5 minus the square root of 3. Over 5 minus the square root of 3. And that's going to set up a difference of squares, which you're going to see in just a second. So in this case, it's really simple. The numerator is simply going to be 5 minus the square root of 3. And the denominator, we'll use FOIL method. So we'll say, okay, 5 times 5 is 25. 5 times minus the square root of 3 is minus 5 times the square root of 3. Then I have the square root of 3 times a positive 5. That would be plus 5 times the square root of 3. And lastly, I have the square root of 3 times a negative the square root of 3. That would be minus 3. So in this case, the minus 5 times the square root of 3 plus 5 times square root of 3 go away. And all I'm going to have in the denominator is 25 minus 3. That's 22. And my numerator will be 5 minus the square root of 3. And that's as simple as that's going to get. So that was similar to what we've used before quite a bit. Is adding and subtracting. So notice what we have here. We have an addition and we have a subtraction. Subtracting stuff. So we're not going to be doing any multiplication. But for me to add two numbers together like this, they have to have the same index and the same number under the radical, just like x's. So if I could get the fourth root of 10 and the fourth root of 10, basically this is 1 fourth root of 10 plus 7 fourth roots of 10. I get 8 fourth roots of 10. Okay? On the next, it doesn't matter even if they're in rational exponent form. Here I have the same base, 8 and 8, the same exponent, 1/5 and 1/5. So because those are the same, then this would simply be 12 times 8 to the 1/5 power. Now sometimes we're going to have a situation like the last one where the indexes are the same, but the base, but what the radicands aren't. But they can be made to be the same. So if I can make this cube root of 54 be something like the cube root of 2, then I can actually add these. So what you have to do here is I would take this cube root of 54 and I would say, wait a second, that's 27 times 2. And over here I've got the cube root of 2. Well, the cube root of 27 is 3. So this can actually be changed to 3 times the cube root of 2. Plus 3 times the cube root of, plus 1 times the cube root of 2, and the 3, and of course there's a 1 here, that would be 4 times the cube root of 2. So even though it looked like I couldn't add those at the start because the radicands were different, they actually could be changed so that they could be added.